In this video, we're going to learn how to write a direct proof. So we're asked to use the given information to provide a direct proof of the statement below. Okay, so here's our statement, but first let's look at the idea for writing direct proofs. So you're going to write a lot of these over the semester for the different content in the different chapters. So this is a structure you want to become familiar with. It can seem tricky at first, but with practice and if you follow these guidelines, you'll get the gist of it. So the idea is you're given a conditional statement. So if P, then Q. Okay. Also note that conditional statements are all or universal statements. They're saying that for all elements in some domain, if P is true, then Q is true. Okay. So what we're going to do is you assume that P is true, and then you use definitions and theorems to show that this implies Q is true. So remember, with conditional statements, we learned from logic that if you have a true hypothesis and a true conclusion, then the statement is true. Okay. Make sure to note the domain and ensure your computations and definitions apply for the domain. Okay. So here is the problem we are asked to prove. Prove that given three integers a, b, and c, if a divides b, and a divides c, then a divides the sum b plus c. Okay. Now down here I have the definition of divides. This is in your interactive lesson. An integer x divides an integer y if there is some integer x such that y equals k times x. The symbolic form x bar y is read that x divides y. And here's a quick example. Just note, as noted in the lesson, this is not an operation. You are not being told to divide 4 into 24. I know it kind of looks like if there was a hat on this, it's like long division, but it is not. This is just a relationship. It's saying that x and y have a relationship. You're not performing any operation. So if we're told 4 divides 24, okay, this is an alternative form that's more useful for divides. It means there exists an integer k. In this case, the k is 6, such that 24 equals 6 times 4. Okay, so that's what this relationship means. Okay. Next, we're going to need this fact, and this has to do with the domain. So if a and b are integers, then so are a plus b and a times b. In common language, this means the sum or product of two integers is also an integer. And for short, we say that the integers are closed under addition and multiplication. Okay? This is important because we want to make sure that our result falls in the domain. If we're talking about integers, if you divide 5 by 7, although 5 and 7 are integers, the result is a rational number of 5/7, which is not an integer. Okay, so these are the two things we need. So let's kind of partition this sentence to get the gist of what we need. So here are the three main components. We're given three integers a, b, and c, so that's referring to the domain. Okay. Here's the hypothesis. If a divides b and a divides c, so this is the part we assume. And then we want to show that this implies a divides b plus c. Okay. So you're going to start by stating that we have three integers, a, b, and c, and assuming a divides b and a divides c. So you start a proof by writing proof. Okay, whenever you're asked show that or prove that, you're writing a proof, and then you write a semicolon or a colon. Okay, now we state let a, b, and c be integers. Okay, that's what we're given, our domain. And suppose that, so this is the part where we're assuming that a divides b and a divides c. Okay, now you want to write in some alternative form, or you're going to use algebra. Here we're using a definition. We're going to write more of what it means for what we're assuming to be true. Okay, and then our ultimate goal is to get to the conclusion. Okay, so you may not see it all right away, but you want to start by writing these in terms of the definition. So I've written these two statements in terms of the definition. Okay, so since a divides b, there exists a k sub 1. So when you're using multiple variables, you want to use subscripts so you can tell one from the other. So there exists a k sub 1 such that b equals k sub 1 times a. So that's directly from the definition. Okay. Also, since a divides c, there exists an integer k2 such that c equals k sub 2 times a. Okay. So now we have these in alternative form. And at this point, I stopped and I said, okay, where is it we want to get? We want to use this information to get this. And what does this mean in terms of the definition? So I wrote that down here. This is what we want. Now, don't put this in your proof. Okay, we're going to use a bunch of steps to get to this, and this just lets us know kind of what our goal is. So we want an integer k such that b plus c equals an integer k times a. So that's our goal. Okay. Well, now we have these two equations, so let's write b plus c in an alternative form. So using the equations, we have b plus c, so I took this expression for b, it's k sub 1 times a, okay, plus I took this expression for c, k sub 2 times a. Okay. So notice it's starting to look like this. We need an integer k, and we have, each of these terms has a factor of a and other integers. Okay, so why don't we factor out the a, okay, and then we'll have a times k sub 1 plus k sub 2. So factoring out the a gives b plus c, that's the left-hand side. I factored out the a, and usually in algebra we put the a out front, but I put the a as the second factor so it corresponds more closely to our goal. Okay. Either way is fine, multiplication is commutative, but make sure you use your parentheses. So it's the sum of k1 and k2 times a. Okay. So we're almost there. Okay. All we need to show now is we want an integer k, and instead we have this k1 and k2. Okay. But we know that k1 and k2 are integers. Okay. And we know based on this fact, this is why this fact is useful. You may think, oh, you're all done, you got it, but you have to be able to state that this is in fact an integer and not a rational number or a square root or something. Okay. So since we have a sum, we'll say that since these are integers and integers are closed under addition, sorry, we're adding these two here. There's another number, k, that's an integer that equals this. So that's what we're going to write next. So we write, since k1 and k2 are integers, their sum is an integer since addition is closed under the integers. Okay, so don't forget this statement. You have to show you're still in the domain. So we'll define a new letter k. We'll say it's the sum of k1 and k2, and this is just to clean it up and get it in the nice form of the definition. And then we have that b plus c, replacing k1 plus k2 with k, is k times a, where k is an integer. Okay, so now we know by definition k divides, a divides b plus c by this definition, and we're done with the proof. So let's write that. And now we state our conclusion. By definition, this means a divides b plus c, which is the desired result. Okay, and at the end of proofs, we usually put a little square that we color in, but that's hard to do on the computer. Or another thing we do is we write QED, which is Latin for, I'll let you look that up and Google it, for fun. Okay, this lets us know that you're done with the proof. Okay, so just to summarize, when you're writing a direct proof, okay, make sure you note the domain. You start by saying that the values you need exist and define them. Okay, make sure they're in the domain. Okay, then you assume the hypothesis. You use definitions to write this in an alternative way. Okay, note that you're trying to get the conclusion and not directly in the proof, but kind of on the side. Write it down so you know where you're going. Okay, then use the definitions to rewrite the hypotheses and transform your equations or expressions or whatever you have into the form of the conclusion. Okay, make sure you state information about the domain if necessary, whether it's closed under addition or multiplication. Okay, then make sure you conclude and state that you've proven the desired result. Don't do this without proving it. I've seen students just write this part and skip the middle part. This middle part is where you're explaining how one part gets to the next, and then you can write QED to conclude.